Okay, welcome to the first non-keynote session of TyDe. We're going to be talking about usability testing and static analysis. And we can get started with Skye Soss. Welcome.
Hi, so I'm here to present about a type and control flow analysis for System FC, and this is ongoing work with my advisor, John Reppy. So this talk is mainly a culmination of two existing works, which is a control flow analysis with type flow analysis as well for System F by AdSit and Fluit, and the System FC work, which is by Solzman and all the collaborators, and it's been extended since. So what I'm going to do is I'm going to talk about how control flow analysis is normally implemented, how the type and control flow analysis improves on this by using types, what System FC gives us, and then finally how we can use these all together to improve how programs are optimized. So with control flow analysis, in the setting of functional languages, the really important question is what values can each variable take on over the course of running a program? And specifically, what we really care about is which lambdas can flow to each variable. So here's a program that we're going to be using as an example. And it's sort of the hello world of higher order control flow analyses, where you have just an identity function that's being applied to two different functions. So even though there's a lot here, the really important bit is here, which is where we actually are applying the identity function to arguments f and g. F and g are both functions, and the way that they're implemented is sort of not necessarily relevant here. The important part is the types and the fact that these are functions being applied. So if you just take a look at this code and you know a little bit about how Haskell works, I'm sure you're able to determine what values each one of these variables can take on, because each one will basically only be ever assigned one value over the course of a program. But in general, you can't do that with a computer because you need to make sure that everything is finite. So to efficiently implement a control flow analysis, what we're going to be doing is flowing values from the literals throughout our program until they finally reach all of the variables in our program, and then once we reach a fixed point, we stop. So to start out, we need to indicate where all of our literals are. So here I've highlighted all the literals in our program. So this is all the lambdas, and then the two literals at the bottom. And in the first three cases, we immediately bind them to a variable. So this is the part that we're sort of noting that these lambdas are immediately bound to these variables. And there's one other way that variables can be assigned values, which is where we have these call sites. Here I've highlighted all the call sites, and here for a value to flow into the variable that's being assigned the result of this call site, you pick one of the lambdas being bound to the function, one of the lambdas being bound to the argument, and you, in some sense, step that evaluation one step to figure out what happens. And then the result flows into the result value. So what does this look like when we actually want to run this? So before we run this, I'm going to use these lambdas with a subscript just to keep the size of these literals smaller. So to start our analysis, we start with basically a hash table that maps each variable to the possible values it can take on. We started out by noting all the literals, which includes the identity function f and g because they're immediately bound. So we add those to our hash map. Then we can take a look at this call site here, and we can see that both the call and the argument are inhabited. So we can take a look at what happens when we call the lambda ID on argument lambda f. So importantly here, this will flow the value in variable f into the variable x. So we store that there. And the same thing happens in this other call site, where we say whatever is bound in G is going to flow into X. Then we know that the result of the identity function flows into f prime and g prime here. And we know that x is going to be the result of ID. So what we can do is we can say, OK, the result of ID flows into this variable here, so we can copy over the lambdas. And immediately you can see that we sort of are over-approximating, because when you really execute this program, you don't get this behavior. So stepping through the rest of this program, you'll end up getting something that looks a little bit like this. I'm sort of leaving these primitives unevaluated, but if you want to reduce the parts that actually do get reduced, this might be your final result. However, we do have some stuck terms here, which is things that we can eliminate with our next strategy. So that sort of control flow analysis works really well when you're in an untyped setting. However, we notice that we have some stuck terms at the bottom, and we can do better because we know that our language is type sound. We'll never have an application of a lambda to an argument that doesn't match types. So in this case specifically, we can take a look at these bottom two cases where we have these stuck terms and sort of just immediately say that this can't happen. And by saying it can't happen, we can just remove it from our hash map. However, if you notice, we have these variable assignments, and these variables actually have types. So this f prime variable has type int to int, but this lambda g does not have type int to int, so we're able to remove that as well. And we can do the same with g prime, and because we no longer have that flow, we would have never gotten these two assignments either, or they also don't match types, so we can remove them anyways. And as a result, we've sort of pruned all the information away so that our final answers, res1 and res2, actually completely match the evaluation semantics. So we've completely recovered all our information. So one way to sort of visualize that is when you think through this problem, or when you actually execute this example program, you have two different copies of x. Every time you call the identity function, you allocate a sort of new version of x, and that's what ends up flowing to the result. But if you want to do things efficiently, and you have to sort of merge values together because you are inherently doing an approximation, you end up merging this x, which causes you to sort of flow all the values to both f prime and g prime, even though that's not really what you want. But by using type information, we're now able to actually distinguish the results that come out of this x after the fact. So as a result, we're able to recover all of our information that we lost by storing everything into one big bucket, which is basically what x is bound to. So this works really well when you have ground types that you're comparing. Here's the same example, but I've removed some of the code and I've expanded out sort of the underlying system F language that we're working with here. So here I have an explicit binding site for the type variable A. And I have type assignments or type applications on the identity function as well. So something that I didn't mention is in the previous example, we actually have an application of ID to F. And what that causes is it causes the value bound to F to flow into X. And if you look at these types, they aren't exactly the same, because one of them is a type variable, one of them is ground type. So why are we allowed to flow F into X? So one way to say that is just to say, oh, if you reach a type variable, it's always OK. But you can do better than that. So just like we tracked all of the flows of variables, we can track the flows of type variables. So here's effectively an extension of our hash map as before, but now we actually have type variables as our keys. Here we have a type application, and this type application is going to bind the type to this type variable binding. So we add that into our hash map. And the same thing in the second case as well. Now, when we ask the question, is X and F compatible, or can I assign F to a variable whose type is A, you can look into the map and say, okay, we have something bound to A that matches this type, we're going to allow it. And if that wasn't the case, you can disallow it. So this is the notion of type and control flow analysis. And this is mostly to do with how you check things are compatible with each other. And this involves looking at a value, asking what type it is, and comparing it with the variable that you're assigning it to. So I'm going to take a little detour here and discuss a little bit about systemfc, in particular some language features that could be improved by our new analysis. So something that systemfc lets you do that normal systemf doesn't let you do are features such as associated types. So in this example, I have some code where I have a type class called listlike, and this is supposed to represent some sort of container type. And the interesting thing about the container is that a container has elements. So we have an associated type called lm, which represents what is in our container. And I just have an example function called first that perhaps grabs the first element of this container. But interestingly, if you look at sort of the implementations here, you can implement this for a polymorphic type such as list, because list is listlike. But you can also implement it for other things that are potentially monomorphic. So in this example, text is a UTF-8 encoded string, and a char is a code point. So this inherently does something more interesting when you ask for the first element. So what does this sort of look like when you write code like this? So in Haskell, you can write surface level syntax that looks like this. And this will type check. But interestingly, if you look at the type of my lm1, it doesn't actually completely syntactically match the type of the expression. Because the type of the expression of C as a character is a character literal as type char. But the type doesn't match that. And this is true in the surface level syntax, but it doesn't, it's not entirely true at the underlying intermediate IR. So in systemfc, this is what the code that gets generated when Haskell type checks, or I guess infers arguments to your functions. In this example, I'm omitting the definitions of this coercions, of all the coercions gamma, and I'm just focusing on the kinds of those expressions. But the way that you can read this is in the first example. You have some character that's being coerced into a different type. And you have a witness that this coercion is valid. And in this context, in the first example, you have character to element of list of car, which does match according to our definition from before. And importantly, if you look at the second example, you don't actually have to apply the coercions on the type itself. You can apply them as deeply nested as you'd like. And we're going to take advantage of that when we go into implementing the type and control flow analysis. So this is the primary aspect of our work, which is extending the type and control flow analysis to work with systemfc. And this involves adding all the coercion mechanisms to how we treat values. And what does this really give us? So in this code example here, I'm trying to mimic the first example. So we still have the same source language code in the sense that we have two different functions that we're each applying as arguments to the ID function, and then we're getting something back out. But unlike the first example, everything seems to have the same type. However, one possible interpretation of this into systemfc actually allows you to treat these as separate types. So this is a lot of code, but sort of the really important bit is that you have these two types being completely different, where the type application of ID is either to list of C to maybe C, or list of D to maybe LM list of D. So even if C and D turn out to be equivalent, these two are going to be considered different. And that's because the result of the first function is always going to mention LM, and then later has to be coerced. So you can delay that coercion until after you've filtered it through all these polymorphic functions. So to sort of shortcut everything, you get results that look somewhat like this. And importantly, if you look at res1 and res2, first of all, they don't end up colliding even though they both have the result from ID. And the second thing is that we actually have tracked this coercion as part of res2. This is what makes type checking work, because when you ask for the type of a value, you need to make sure that you're respecting the coercion when you return the type. All the handling for the coercions is in the paper. So to go over a quick example of one potential use case of this is optimizing the source representation of programs. So here I have an example Haskell program that someone might write where you have some sort of summation over a list. However, if you're a Haskeller, you might say, this plus and 0 is really a monoidal action, and I really want to write this as mconcat because I don't know why. However, int does not have a monoid instance, and instead you need to use this sum new type. And the sum new type allows you to actually write a monoid instance without incurring extra runtime. But your result sort of looks way more complicated and involves coercing. And this is sort of what the code really looks like. So I sort of did the step of GHC here, and I sort of manually compiled the code. This is sort of what the core that gets generated looks like. And as you can see, there's a lot of code here. But really, this is the only important bit. Everything else is just coercions. So what we really want to do is we want to get rid of all these coercions. And something we can know, because we have the type flow information, is all the places that sum is actually used. So in this code example, assuming that this is all in one module, every single time that sum is ever used, it's applied to an argument. That argument is going to be an integer, and it's fully saturated. I guess the fact that it's integer probably doesn't matter here. But because it's fully saturated, you can actually generate coercions for each one of these types and just apply them in reverse. So something that might generate code somewhat like this, where you can coerce everything from the sum back into an int, in which case you generate all these coercions, but importantly, these coercions are sort of inverses of each other. So we might be able to just cancel them out. And now we're back to our original code example, and we've implemented everything in a really nice Haskell-y way without incurring any sort of cost for GHC. So this is ongoing work, and currently the main aspects that we're working on is formalizing this and getting an empirical evaluation going. But also that last aspect with coercion removal, there's also a notion of coercion simplification that's mentioned in the abstract that would also be great to be able to formalize. Then the last thing is to update this to the most recent version of systemfc, because currently we are using the original version of systemfc. And since then, kind coercions have been added, which adds a whole nother level of complexity. Thank you for listening to my talk.
So, any questions? As usual, there is a mic here.
Thanks. I'm interested in your use case.
Mm-hmm.
So, do you want to go back a bit? So you had,
yeah.
you had a kind of overloaded version. The version you started with, I guess before that, with the mconcat in it.
Oh, this one?
I guess this one. That's cool. That's using getSum, right?
Yeah.
Are you saying you're going to transform that version into the one that used list.foldl instead?
Yes.
Aha. So, but getSum doesn't use list.foldl. It uses some kind of overloaded thing.
Yeah, it's the mconcat. That's the thing that turns into the fold. The getSum turns into just a coercion.
Okay. So then you're going to do flow analysis. So and then can you show that? That's right. This code, yeah.
Yes.
So if we compile this code, it'll generate some machine instructions.
Yes.
Right. If you take the version you transform it into, my guess it'll generate the same machine instructions.
It will. So it will generate the exact same machine instructions, but the thing is, it will generate very different core.
Okay, so it looks different, but but that's because it's got lots of types clutter.
Yes.
But in the end, you're going to do a whole flow analysis. It's getting rid of some clutter, but then it ends up with the machine code.
Yes,
So,
well,
you know,
so-
maybe you sped up the rest of the compiler, but that's about all?
No, so this is a sort of interesting use case just for systemfc, but type and flow analysis has uses just for general program optimization. So if you want to do anything like, for example, if you want to figure out that something might be better specialized because it's only instantiated to different types.
So this use case isn't one that's very important. You're saying the other use cases are
this
the
is just
important ones.
the one use case that does not apply to anything except for systemfc.
I see. Okay.
Yeah.
Good. Thank you.
So your talk reminded me, in the introductory examples, of monomorphizing polymorphic programs. So that's something you could do, and you just make multiple copies of each polymorphic function for each type at which they're used.
Yes.
And I have the impression that you would get the same results from flow analysis if you monomorphize the program first. Except, of course, if there's polymorphic recursion,
Yes.
in which case monomorphizing would fall into a loop.
Yes.
So my question is, if there's polymorphic recursion of that sort, will your flow analysis fall into a loop? And if not, why not?
Yes, so it does not fall into a loop, and the reason for that is that types, as they're being tracked, actually refer back to themselves in the store or the hash map. So if you have something where, for example, you have some sort of list type where maybe the list gets instantiated of an infinitely deep nesting of list, that will be solved by effectively you have the type variable mapping to list of A, and then A will point back to the key in the hash map. So you solve this by effectively building a graph instead of building a tree.
Okay, thank you.